Now we can do stoichiometry with gases the same way we would do stoichiometry with solids, except that instead of using grams and molar mass, we are going to have to use this to get moles, obviously. We're going to have to use PV equals nRT to get moles. But the process is still the same. You're going to have to try to figure out of how many moles of what your starting material is. You're going to use the ratio to get moles of what you need. And then you're going to finish the problem. To get to moles, you might have to use PV equals nRT. You may have to use grams and molar mass. This is going to be our ratio. And here again, this could be grams and molar mass, or it could be PV equals nRT. So we're going to have some more options as we go through and we do stoichiometry. Grams to grams or moles to moles in a balanced equation. So what do we know? We know that since we have PV is equal to nRT, with everything else being the same, we know that volume is directly proportional to moles. This is really helpful because if we take a look at gases, and let's say that we have nitrogen reacting with 3 hydrogens to make 2 ammonias. If we look at our gases, with again everything else be the same, we could do this with volumes. If this is 1 mole, 3 moles making 2 moles, this could also be 1 liter with 3 liters making 2 liters. Volume is directly proportional to moles. So we can play with this, and we can play with this at STP. STP sort of saves us a step on using the ideal gas law. We remember at STP that the volume of any ideal gas in liters is 22.4 liters for every mole of any ideal gas. So with any other equation with stoichiometry, we're going to start the same way. We are going to start with a balanced reaction. So magnesium, as a solid, reacts with hydrochloric acid, aqueous, to make magnesium chloride, which is ionic compound and it is in water, so it's soluble, plus hydrogen as a gas. Now, the only thing we can use the ideal gas law, or 22.4 liters per mole, is hydrogen because it's the only gas here. So what do we know? We want to know how many grams of magnesium. Well, we're given 45 mils of hydrogen. Well, we know that if we have 45 mils of hydrogen, we know that there is 1 liter for every 1,000 mils. And we know that there's 1 mole. This is a gas, so we can use our equation here of 22.4 liters, so 1 mole for every 22.4 liters, and this is going to give us the volume, or excuse me, the moles of hydrogen, and that's going to be 0.00201 mole of hydrogen, okay, because 22.4 liters per mole. Our equation is 1-to-1, so we're going to have 0.00201 mole of magnesium, and now we have to finish the problem. Because magnesium is a solid, we're going to ask for grams. We're going to get the molar mass. The molar mass of magnesium is 24.3 grams per mole. And if I multiply this through, I'm going to get that we are going to need 0.0488 grams of magnesium to make 45 mils of hydrogen at STP. All right, so what volume of carbon dioxide produced at 37 degrees Celsius in 1 atmosphere, or can be produced when 5.6 grams of glucose is used up? Now, glucose is a solid. We're going to have to balance our equation. When we balance our equation, we're going to get 6 and a 6 and a 6. Remember, step 1, always balance your equation. Make sure that your units are in the correct values. 37 degrees Celsius is the same as 310 Kelvin. And now we can do some work here. We know that we have 5.6 grams of glucose. We can calculate the molar mass. There's 1 mole of glucose for every 180 grams of glucose. And that's going to go from grams of what we have into moles. But we need carbon dioxide, and we know there's 6 moles of CO2 for every 1 mole of glucose. And when we multiply that through, we are going to get that we have 0.187 mole of carbon dioxide. All right, now, once we have moles of carbon dioxide, we've used our balanced relationship, our balanced reaction, to go from moles of one to moles of the other. Now we're going to figure out how much product we have. We have to go from moles to the volume in liters. Please note this is not STP. And because this is not STP, we have to use PV is equal to nRT. So let's plug some stuff in. We're solving for volume. Volume is equal to nRT over P, which is equal to 0.187. And we have to use carbon dioxide because it's the only gas here that we're measuring. Moles of carbon dioxide multiplied by R, 0.08206 liters atmospheres per mole Kelvin, multiplied by our temperature, which is 310 Kelvin, divided by the pressure, which is 1 atm. To finish with this, we're going to get the the volume of carbon dioxide is equal to 4.76 liters. All right, now, what if we have more than one gas? So one of the keys on gases is the fact that the volume of the gas is assumed to be negligible, which means if we look at any given container, the gas that we put into it feels that the container is zero. These little molecules that we have in here don't really occupy any space. What does this tell us? This simply tells us that if we want the pressure of a gas or gases, we are simply going to add up the pressure of each individual gas. So if I have gas A, B, and C, and I want pressure total, it's going to be the pressure of A plus the pressure of B plus the pressure of C. And we will simply add these guys up. Now, obviously, in order to add up the pressures, they have to be in the same containers, which means the volume is the same, and they have to be at the same temperature. Obviously, if they're not the same temperature and container, they're not the same stuff, and you can't add the pressures up. Now, we also know that PV is equal to nRT, and P is directly proportional to the number of moles. So in order to do this, we can also take and get that the pressure total is equal to the sum of the moles multiplied by RT over V. Okay, moles and pressure are directly proportional. So if we want pressure in a container and we have individuals, we can simply add them up. So I have a sample of natural gas. Natural gas here is going to contain methane, ethane, and propane. Now we've been told here that the pressure total is equal to 1.37 atmospheres. And what we want is the pressure of the individual propane. Now that's called partial pressure, and that is simply the individual pressure of a gas. And note we haven't got volume or temperature, so in order to do this, we are going to have to relate moles to pressure. Well, we know that moles and pressure are directly proportional. So if we take a look at our moles, if we know how many moles of propane we have, divided by the total moles, that's going to be the same as the pressure of propane over the total pressure. Okay, our fraction is the same because everything else is the same. Moles are directly proportional to pressure. So if we take 0.116 moles of our propane and we divide it by 8.24 plus 0.421 plus 0.116, which is the moles of gas total, that's going to equal the pressure of propane divided by the total pressure, which is 1.37 atmospheres. Again, the fraction of moles is the same as the fraction of pressure. And when we solve the math, we're going to get the pressure of propane is equal to 0.0181 atm. And we could solve for any one of the gases in here in terms of its partial pressure. Now, there's a special case of gases adding up, and that is collecting a gas over water. In order to collect gas, somehow you've got to take and force it into a certain space so that you can measure its volume. So one of the ways that we do this is we allow a reaction to go. We have it in a sort of a sealed container such that the gas itself can escape. And where it escapes, it's going to go down this tube And in here, you would start out with this entirely full of water. And as the gas goes in there, it's going to push the water down. And the volume of water displaced, pushed down, is going to equal to the volume of the gas collected, which sounds all well and good, except we've got one problem. And that is that our pressure total in our container is going to equal the pressure of the gas that we want plus the pressure of water vapor that is in that container. Now we know that water likes to vaporize, and as the temperature goes up, the pressure of the water vapor is also going to go up. To get it as high as 100 degrees Celsius, it's going to be boiling, and the vapor pressure or the pressure of the gas will be 760 torr. So if we want to look at how much gas we collected, we are going to have to take the total pressure and subtract how much of that is actually water. So the pressure total is equal to the pressure of the gas that you collected plus the vapor pressure of water. And you're going to look that up. Just take a temperature and look it up. If you saw a graph of this, and this is your temperature and this is vapor pressure, this is a nice exponential, and you can take and look it up as a function of temperature. All right, so we're collecting some oxygen over water. So when we collect our oxygen over water, the oxygen would have been bubbled in. There'd be some water here, and we'll find that we have 193 milliliters of oxygen. Our temperature here is 23 degrees Celsius, which is the same as 296 Kelvin. Now, not only do we have oxygen in here, we also have water vapor. Okay, and the pressure total, which by the way is also going to be the barometric pressure, because if it goes above barometric, it explodes. That's always a bad idea. Our pressure total is 762 millimeters of mercury, and that's going to equal the pressure of oxygen plus the pressure of water, or the vapor pressure of water. So if we take 762 and we minus 21.1, we're going to get 741 millimeters of mercury for our pressure of oxygen. So we keep going here, how many grams of oxygen were collected? Well, this is a gas. And if we've got a gas, we know we can use PV equals nRT. Everything has to be in the right unit. So let's take 741 millimeters of mercury, 1 atm for every 760. And that's going to give us a pressure of 0.975 atmospheres. Our volume is 193 mils, which is 0.193 liters. Our temperature is 296 Kelvin, and if we have this information, we can solve for moles. Since PV equals nRT, then N is equal to PV over RT, and we can plug this in. 0.975 atmospheres multiplied by 0.193 liters divided by 0.08206 liters atmospheres per mole Kelvin times 296 Kelvin. So we're finished this, we're going to get that the number of moles is equal to 0.00775 mole of oxygen. Well, let's finish this problem. If I have 0.00775 mole of oxygen, I know there's 32 grams per mole. And when I finish this up, I'm going to get 0.248 grams of oxygen.